Welcome back to Compute 653. I'm Aaron Zianze, and today we're going to be presenting our project, which is a survey paper on loop transformers and the latent space reasoning that these loop transformers can introduce, right? So I guess we start with our motivation for why we choose loop transformers. So in our previous presentation, we sort of came to this nice result from Merrill and William Merrill's paper about how the expressivity of transformers using chain of thought, decoder-only transformers could essentially allow you to simulate Turing machines, right? And we were more inclined towards looking at this part rather than that part. So chain of thought, in its first introduction, was sort of evolved as this reasoning scheme, right? I think the paper is also called chain of thought prompting elicits reasoning from large language models, in which you could just make a transformer or any large language model do some autoregressive token generation with, ask it to do it in the prompting, and it could elicit reasoning behavior for like math tasks, other algorithmic tasks, symbolic reasoning and stuff. But some of the newer papers, such as this one called Descartes or not Descartes, show that this chain of thought reasoning is mainly good at symbolic reasoning and math, like grade school math questions. And another paper came out around the same time from Meta, which showed that reasoning using this looped transformer architecture could sometimes be more powerful than just chain of thought. And we'll get to why, because that's one of the papers we're presenting. So we look at this loop transformer architecture and basically ask some questions with what can we do with those loop transformers, right? And so we found many works, both empirical and theoretical, about how with these loop transformers you can do algorithmic tasks that involve like iterative computation. You can do like general program execution if you have some sort of instruction set architecture that can be done using a transformer. You can do reasoning, which is one of the topics we're going to be covering today, and we can do length generalization, or you can achieve this length generalization behavior to some extent with loop transformers. So we're going to be presenting two main empirical and slightly mixed with theoretical results if we have the time. And the first paper is called Training LLMs to Reason in a Continuous Latent Space. And that's by Howe et al. 2024. Or 2025. So let's just give a bit of background for this paper. So their main inspiration comes from how with chain of thought decoding and reasoning, you're slightly restricting yourself to being able only to reason in the language space, because the way transformers work is they really want, or large language models work, is they really want to be, or really want to have coherent speech, right? Unlike me. So let's say you prompt an algorithm, a large language model to do some task, say like a common word problem where it's like, okay, Jimmy has 5 apples, he lends 5 apples to his friend, buys 4 more apples, how many apples does he have? Something like that. And if you do it in like the traditional prompting scheme, you'd have something like, let's do this step by step, right? And it has like, okay, Jimmy has 5 apples, and then some other more tokens, and then buys, wow, I think it's not right. Buys 4 more apples, right? And so on. And then it comes to like an answer token at the end. But what we're doing with just regular chain of thought is we're assigning the same compute budget of like one transformer call to this let's token do this step, where the only really challenging tokens that it needs to generate on its own are like something like 5 apples or like buys 4 more apples, right? So that it can come to like abstract this word problem into a math problem. And so if we look at just the traditional transformer architecture where you have, or chain of thought prompting, you have, this is your transformer, you have some input to it, so your prompt, that has to go through this token embedding layer. So let's just call that TE, and then maybe you have a position encoding also. this is your embedding. You feed that to your transformer will output something in the embedding space, so like whatever RD that is, and you need a language model head, which looks at the vocabulary and finally gives you an output token, say XI, right? Then you feed that XI back in over here. It does the same token embedding, position embedding. You go to that transformer, you get another output embedding, and then you get the next token. And that's how it works. So, okay, this is X1, sorry. X, okay. And you continue doing this. So you're assigning this same budget for each token in your language space, when you could be doing something a bit cooler. So let's see what they do. They say, using this looped architecture, we'll introduce this new form of recurrence where instead of getting a output token explicitly, I will just erase this part. I'll feed the output embeddings that I got from that layer straight back into my transformer. So I'm going to skip the language model, I'm going to skip the language model head, I'm going to skip the token embedding phase as well. And I'll keep doing that before I eventually output a token. Alright, so boom, boom. And then at some stage, I'll get how you get this. You finally get some output token, say X after K stages, right? And so what you're doing is you're basically, in a sense, allocating more compute budget and more transformer calls for the same output token. And I'll get to why this could be useful now. So,
is this like a transformer with more layers, but there are some parts of the transformer that are like each other? They are similar to each other.
No, it's just a fixed layer transformer. You keep feeding that same output embedding back in as input embedding. So you skip looking at their token embeddings and like their vector embeddings, that you skip doing the position encoding part. You just feed that output embedding from the last hidden layer back to the first hidden layer.
I see. For example, if you're feeding it twice, it's like having initially it's like having a transformer with 2 times more layers.
Yeah.
But instead of training that big transformer, you're just training this little one.
Yeah. So you're doing a lot of parameter sharing.
I see that.
Yeah.
Can I say something?
Yeah.
It sounds like this is backpropagation, leads to backpropagation through time, which has a terrible complexity as the number of time steps goes increases.
Yeah. So
is that going to be addressed in some way?
They don't really do backpropagation through time for this, at least. I've seen some other papers with the same architecture doing that, but for this they just skip training over the latent phase. So I'll go through the training of this.
I see.
Right now. Yes.
So they sort of take a shortcut.
Yeah.
Okay. All right.
They sort of take a long cut actually, because they're doing more of these forward passes for the same number of tokens. So it's computationally more expensive, but they're saying that if we do this allocation, we can maybe get better reasoning, which the result can show that. I'll get to that soon. Yep.
So to be precise, you're saying that they train by actually tokenizing and untokenizing.
Yeah. Yeah.
But they just.
Oh, can you repeat the questions, because if it's the mic is
we're
facing the other way,
so
I can't hear it.
The question from Paul is whether they're training it after like tokenizing it and untokenizing it, which in a sense they do. So let's look at their training phase, right? So just as an aside, they call this chain of continuous thought, right? Which is okay, correct, nice name. And then they abbreviate it as this, and this to get the name coconut for their paper, which whatever. So the way they train it, so I'll just write training, is they'll have initially like chain of thought data, right? So that's say prompt, and then you have stage 1, stage 2, all the way to some stage N, and then your answer. And then they'll do curriculum training. So in the first stage of their curriculum training is just this chain of thought data, which has the intermediate supervision of each step. Then they do this stage 0, where they have the same prompt, and then they replace stage one, or no, they don't replace it. So they introduce this BOT and EOT token. So what that means is beginning of thought, end of thought, right? And then it's the same thing from stage one all the way till the answer. In the next stage, so this is stage 0. In the next stage, let's call it stage 1. What they do is they keep the prompt, and then they replace stage 1 using that BOT and EOT again. But in between the beginning and end of thought, they're going to do some of those loops, right? And they say that they replace in the kth stage of curriculum training k of these, and they replace them with k times c continuous thoughts. So these are c's, right?
What is Q?
Hmm?
Can you define that?
What k is?
Yeah.
Okay, so k is just, we get to some stage k, right? We're replacing k of these with k times c continuous thoughts. So c loop iterations, right? And so what they have to do in each loop is actually, they do have to like output it to the language model head just to see if it gets to this end of thought, so then they can exit it, right? Because they're sort of like switching between this latent phase and then going back into language generation, so that's like a language phase, and they call that language phase and latent phase. So that's their training speed.
Okay, can I have some clarification questions?
Yes.
I'm not sure I fully understand it. So it's a data manipulation scheme. So you start with a trained model, and it's fine tuning,
Yes.
right? So you do the chain of thought prompting. It generates this lengthy response. Somehow you segmented it into stage 1, stage 2, stage, and I don't know what those are.
Yeah.
And then an answer comes. So you were asking it to break it into steps or something? Like what are the stages like in the
These stages
first
are,
line?
I believe they say in the paper that they're simply just tokens. So they're like the
Just the
intermediate
tokens,
steps. Yeah.
okay.
But it
Alright,
doesn't really make sense. I don't understand why they have to replace them before doing the chain of thought, or the latent thoughts. But they do it, at least in their diagram that describes it.
They're replacing what?
They replace this stage, which is like the token, I guess.
Okay.
But the way they then calculate a loss is just from that answer they backpropagate and they ignore the loss for these latent thoughts. Which sort of.
No, okay. So like let's go to the, okay, so then we generated this data. And we're gonna use this data to sample, do this refining or like fine tuning of the model by generating new data for supervised learning, essentially.
Yes.
And okay, so the stage 0, maybe stage 1 could be more interesting. Because at stage 0, like they repeat a prompt. Of course, you're not training on a prompt.
Yes.
And then you'll insert these special tokens. In between the special tokens for stage 0, there is nothing.
Yes.
And then you repeat the whole like stage 1, stage up to n and answer after that.
Yeah.
And that becomes part of the training data. And the supervised training loss is going to exclude everything up to from the prompt to the end of those token.
Yes.
And it includes everything else. So that would be more like just a regular chain of thought training, right?
Yeah.
This chain of thought data. And then more interesting thing happens with the stage 1. So in stage 1, they take this model that was trained, or we don't know how many iterations, and they're gonna fine tune it. In this fine tuned version, there is something between the beginning of thoughts and end of thoughts that I didn't quite understand. Like there is maybe one internal like step that was made that didn't really produce anything, or it could produce something, but we would ignore it anyways, right? And then you repeat stage 1, stage 2, stage n after the end of thoughts token, or like what's the data that comes after that?
I guess
or you leave out stage 1?
Yeah. I guess the loss is still like propagated
No,
somehow.
so first, what's the data? What's the data for stage one?
For stage
Like,
one.
can you write out
Yeah.
exactly how the data looks
There
like
wouldn't
for that?
be any like
Because
data
you just
for
wrote
this
dot
part.
dot dot, yeah.
Yeah,
Like,
this would be
it's
like
confusing.
stage k plus 1, I guess. Stage k plus 2, all the way till stage n,
Okay.
and then the answer as well. So
Let me see.
Mhm.
So, stage, what is test? Or what did you write there?
K plus one. K plus
K
one.
plus
K
one.
plus
K
one.
plus one.
Yeah.
What is K plus one? We are at
Oh.
stage one.
Oh, okay, for that then it'll be
Wait.
stage 2, so the second token. So they're replacing.
Okay.
Yeah.
Okay. Then we can generalize this to stage K, right?
Yeah.
Okay, I see. So you leave out stage one,
Mhm.
it's going to be like you expect the models to already pick up what to do there,
Mhm.
and then you supervise train it
Mhm.
so that after it's doing its internal chain of thought one step,
Yeah.
it should produce stage two and so on and so forth,
Yes.
right? Like gradually replacing more and
Yeah.
more
Yeah.
of what was produced
Mm-hmm. Yeah. So,
externally. Okay, so that's very interesting, but it's also a little bit weird
Yeah.
because the pitch was at the beginning
Mhm.
that text limits of what we can do,
Mhm.
and in this training we are still doing it like first
Yeah.
generate text and
Yeah.
like you're gradually kind of like a little bit veering off, but like I guess maybe the idea is that like it allows the system to, I don't know, take some, I would still say shortcuts or yeah, like somehow
Yeah.
not to take the same path in producing some answer or the same answer, but yeah, gradually veer off from that path that was
Yeah.
produced at the beginning.
Yes.
I see. Okay.
Yeah. So
Alright.
that's their training stage. But I guess a nice example that they give themselves is that they say that their loop transformer, or not loop transformer, that this latent space architecture basically works as a breadth first search. So they have like, this is their evaluation at the end. And I'll try to wrap this up because we need to present another paper. So they have like this weird, not weird, it's, they prompted with these tokens that the language models have never seen before. So like every grimpus is a yimpus, every gorpus, like some garbage alien sounding words, right? So this thing is one of those things. And at the end they ask a question, so like Alex is one of those, say grimpus. Are they a gorpus or a dorpus? So what they're doing is like they're making this huge, like essentially a graph of like search for the language model. So let's say you start here knowing that Alex is a grimpus, and then this is one of the options, this is the other option. You have a bunch of connections, right? So you have something like this. And in their experiment, they find out that the chain of thought reasoning on a problem like this usually fails and usually picks the wrong option. And they say that this is because the way that chain of thought reasons is too deterministic in a sense, or it's too greedy. So what it does is like, since it has to generate a token in each forward pass, it could generate a high probability token which leads to a wrong result. But what Coconut would do.
Wait. So this is the same example as this star graph example of the force of next token prediction?
Yes. So like say you start over here, Grimpus, and then you have like the two sinks over here, or not sinks, goal states. So I'll just do gold like this. And then Dorpus, let's say.
It's really hard to hear you.
Oh, sorry. So let's say they have this start state, which is what they given as context over here. My bad, I misspelled Grimpus. And then they have the two options that are given as part of the question. So like say one of these and one of these. In their results, they show that the chain of thought doesn't always find the correct option or like traverse this graph correctly such that it finds the correct conclusion for given this prompt. But Coconut is essentially, instead of locking a token in too early with the single forward pass, since it's doing multiple forward passes before reaching a single token, it can generate multiple candidates for the question, and then reason out in each step doing one breath first search, or like iterating over one breath, one depth of breath, right? And that's the result that they get. So they say that this Coconut thing, if you give it multiple thought loop steps, you can sort of encode multiple candidates in your latent space representation, and then with those you can keep iterating with those and then eventually come to a better result than regular chain of thought.
Can I ask a question? Is this a self-improvement thing, or in the training when you build up this curriculum, the stage 1, stage 2, stage and answer, whatnot, are they like part of like the golden answer should look like this?
Yeah, they do.
Because if you recall the next prediction paper, that's how it was, right? Like we want the pass from this to there, and like the very first node is really hard to compute, and like would kind of like these models fail at that. But you can compute it, and it remains challenging to do that, and then but it's not self-improvement, which is not to say that like I don't want self-improvement. It's fine to give the right data to the models. Okay.
They are training
So
on
it's like we give the right data to the models, and the models are struggling to make the predictions, but by changing this training this way, they kind of win. So usually what people next do is that they take measurements for bigger and bigger graphs and larger distances, and then you wonder how does this scale? Like, can it actually solve like this fast finding problems? Or does it have a limit of like 2 steps or 3 steps, or like how useful is this? Did they do any experiments like that?
I can't recall if they did experiments on the depth, but
Okay.
I'll try to look at it. Okay. While I answer this question, I'll just also erase the board for the next paper.
Can I also ask, is this essentially the same as doing chain of thought, but for lots of steps at each stage?
Yeah. It's sort of, yeah.
I couldn't hear the question.
Is this like doing, sorry, can you repeat the question as well?
I asked if this is the same as doing chain of thought, but multiple times at each stage.
It's less of, okay, so in each chain of thought step, you're producing one token guaranteed, right?
Right.
What they're doing is it's like that, except they're doing some forward passes where you never generate the token. You just plug those same embeddings as input embeddings.
So how does the inference look like? Like, is it like constant C steps per token generation?
Yeah. So that's also like another thing. They say like dynamic budget allocation, but then they do specify like a hyperparameter for how many of those iterations you can do. But it's also they at least do it as like a max, but or at least in their training. But what you should be able to do theoretically is like at each of those iterations, check what the language model is producing. If it's an end of thought token, you sort of just exit the latent phase.
So you still follow the chain of thought during inference as well, or do you just generate the output?
I think you'd still be doing the chain of thought with those text steps as well, like with the text, not just this hidden like prompt and then answer. Is that what you're asking?
Yeah.
Yeah. Okay.
Okay.
Yeah. This is very suspicious to me.
Yeah.
And I would think that it should not work on the same example in the stack graphs from this next token prediction paper, right?
Yeah.
This what happens here is that you're building this curriculum, and the first token, to produce the first token, you have to do all the calculations, basically.
Yeah.
And when you're doing this training, the very first thing that you do is that you discard the first token. You're not even showing that, right? Like for stage 1, first token was not given.
Yeah.
So you are supervised training on the easy data. Like after that, okay, maybe the next token is hard to predict. Like stage 2 token is even harder to predict, maybe. But somehow, like, how did we have this, like, figuring out to do all of these things, right? Like, and the rest of the tokens are still easy to predict, and yeah, like somehow it's a bit magical that it works, right?
I'd agree, yeah, because they are replacing those. I'm trying to reread it, and it does say replacing those like intermediate steps completely with this the thought. So I don't know if they say that once it reaches the end of thought, they're trying to produce the same token or not. It's just I'm also a bit unsure on how they propagate that same intermediate steps loss. I think they have to be producing that token at that stage.
Yeah, like based on what you put on the
Yeah.
board, they do.
Yeah.
But then, like, it's a bit hard to understand how the difficulty is overcome,
Yeah.
right? Because, like, for each stage, there is easy parts of the training and hard parts of the training. The hard part of the training is after the end of source token to produce the first meaningful token. And
So, is this okay if,
Right.
if we take it a bit offline? Because
Sure,
Yanzi wants to do the next
Let's move on.
presentation.
Let's
Yeah.
move on.
Sorry
Yeah.
about it. We can talk about it after. Yeah, go ahead. Sorry.
Okay. Okay, so before getting to the main result of the next paper, I'm gonna first motivate you of the loop transformer again, but from a different perspective, which is the length generalization perspective. So forget about the loop transformer for now. Input length is often correlated with the problem difficulty. So if the input is longer, then it's likely to be harder to solve. And we say a model is able to length generalize on a task if it can solve the task on input of unseen length. So for example, in a data set, in a training set, let's say the input length is only up to 20, then it's also gonna be able to perform well on length of 30, 40, or 50. Okay, and then the empirical result of the previous paper shows that with respect to some task, if there exists a Rust-L solution, then the transformer is able to learn this task. Yeah. I'll just do the. It's able to learn this task in a length generalizable way pretty easily. So one example of such task would be finding the mode of this sequence. And that work also shows that if there doesn't exist a known solution, a Rust-L solution, then it's much harder for transformer to length generalize. And then one example of such task is the addition task. And this paper is called loop transformer with length generalization. And then it kind of implies a more general statement compared to this one. So it implies that with respect to some task, if there exists a RASP L based solution, then the corresponding transformer, I'll just say transformer prime, associated to this RASP L based model is able to length generalize easily. Okay, so let's say this addition task. This means that if we can come up with a more complex RASP-L based program that can solve this addition task, then the corresponding transformer prime, is able to learn this addition task in a less generalizable way. So the next question would be, okay, what kind of RASP-L based program is able to solve this addition task?
How do you define RASP-L based?
It's kind of undefined. It's not, this is not a term in the paper. This is what I made up. But it will become more clear after I introduce this RASP-L based program. Okay, but up to here is the logic clear? Okay. I'm asking because this is super implied. It's not like something that they mentioned, oh, okay, this is our hypothesis. And then we introduce the program called N RASP-L. And you can see this is kind of related to the loop transformer. And then we say a program P is an RASP-L program if, first of all, there's a function T from integer stat to integer stat, where this input n is the length of the input. And then T of n determines how many times you can loop. And then second of all, this P, it can be decomposed into, let's say, a sequence of programs. P create, and then P prime, and then P pose, where HP is where P whatever is a RASP-L program. And then it can be decomposed in a way that P create, P prime, and T of the steps. And then the last term is the P pose. So this is what I mean by a more complex RASP-L based program. And then we can show that, I'm not going to introduce the proof, we can show that there exists a RASP-L program with T of n equals to n plus 1 one, such that it can solve the n-digit addition task. We can prove this. Okay, so based on the implied hypothesis, we're wondering, because essentially this is kind of the computational model for the loop transformer, because it has these loops. So essentially, we want to know if the loop transformer is able to learn loop transformer addition task in a less generalizable way. We're wondering if the loop transformer is able to learn addition tasks in a less generalizable way. So, are there any questions so far?
Are there any published results on this?
Huh?
Are there any published results on this question? Or this is completely open?
Oh, this is the paper that we're talking about.
Yeah.
It's called
It's called loop transformer with less generalization.
But like, okay, did they run experiments?
Yeah,
Did they prove that it actually works? There's addition.
They run experiments for this
Yeah.
task.
Okay, and it does work, sort of.
Yeah, essentially.
Do they also prove?
Prove which one?
Do they also prove anything?
They only introduce this model, and then they prove it can solve, this model can solve the n-digit addition task and also some other tasks. And then that's it.
But no proofs about learning or something.
They show that empirically show that you can do the learning with it.
Yeah, they didn't prove why they can do the less generalizable.
They have a training algorithm for an inference algorithm how to do this.
Oh wait, the training algorithm is not the one that you talked about before.
No. It's a much different training algorithm.
Yeah.
Where
Okay.
I think
What is it?
It's end-to-end training, right?
Yeah.
Yeah. It's an end-to-end training scheme. Do you want to write the data set or anything?
Oh, sure. I'm just, is it okay, Chaba, if I erase this?
Yeah.
Okay. Okay, and then we're going to introduce the training and the inference. So for the training, they use the end-to-end training, which means that there's no like training data for the intermediate steps. And then the training data set looks like okay, so this is our input sequence. And then this is our output sequence, which is the label. And then T is the is a predefined number of loops we're supposed to take. And then this Li is the input length. Okay, and then it's kind of surprised because the training and the inference method is kind of simple. And the loss function they use, it just cross entropy loss between these two sequences. Okay. Well, there is some issue about this equation in our opinions, but the high level idea is to. Oh, by the way, you have to loop this for like. Yeah. Just say t times t iterations. This represents the loop transformer output. The high level idea is to you plug in an input, your output, and then the label output, and then you take the cross entropy loss. So this is very vanilla. And then the issue is that the paper we're mentioning, this is what the paper says, not what we say. This n theta sort of represents one round of the loop transformer. It only handles the embedding space. It also says this y sequence is the decoder sequence. And from this part, we can, this one implies that this is the one hot sequence for each token. So the shape of this sequence of vectors is going to be L times the size of the vocabulary. Okay, and then we can also imply that this input here, because this M, it only handles the embedding space, which means that this is the embedded vector. This is the output after the embedding layer, which means that we should have this shape, where D is the dimension of the model. And which means that because of this composition of functions, you can see this also as an input of the first t minus 1 iterations, which means that this, the shape of this is also an embedded vector, so the shape of this is L times D. So basically, we're taking the cross entropy of this and this. Like the shape doesn't even match.
Is this the problem with the inference part or the training part?
The training part.
Oh.
They have the same problem.
Okay.
Like the notation problem where.
Oh, because the inference uses the same notation for cross entropy,
exactly.
right?
Yeah. Okay, so that's maybe one issue that we found in the paper.
Or
Okay, can you break it down for addition? Like, how does this work? Like, what's the X, what's the Y?
the X would just be the
Like this will be x1 and x2, x3, x4.
Yeah.
And then y will be.
Don't you need two numbers
Huh?
to add? Like, we're adding numbers. What are we adding?
What was the question? I think like how do you represent this for addition problem?
32 numbers.
Yeah. Because they do some sort of like they keep the same length, but they do some input padding. So it's like it's x1, x2, x3, x4 plus x like 5 to 8, and then they leave space for the other tokens as well. So it's like they use some padding hash tokens, I guess, for x, say 10 all the way to x 13. So I guess it looks like this. 1, 2, 3, 4 plus 5, 6, 7, 8, 8, equals hashtag, and some additional space, and then they're saying that it can fill in these tokens for the addition, I think, is what they said. Is that it for the presentation?
Huh?
Is that it for the presentation? It's already like 4:20. Yeah.
I'm not entirely sure.
Should we take more of this discussion on offline just so that we can have the next group do their presentation also?
Sure. Just one last question.
Yeah.
Do they do backpropagations through time?
I think this paper mentions that
This
they did,
empty
yes.
model is composed 3 times itself.
Mhm. Yeah.
Okay.
Yeah.
So here they do that.
Yeah, I think they mentioned doing that for this one. Yeah, but I'll get a better answer in the report finally. Yeah.
Okay.
Thank you for this one.
Alright,
Okay.
thanks.
Yeah, sorry about that.
And maybe just one more minute to ask this question. It's like, Papa, do you agree there's a mismatch in their dimensions or in their shapes between these two?
Because
Yeah, I mean, like, the model does something, right?
Yeah, because at least for inference, they say that this is the output for after the t iterations, and then this is the decoded sequence. So they're saying that this is in the like a y hat in the vocabulary space, but then this is embedding space. So they have to be doing some sort of conversion because they're using cross entropy between the same embeddings and then the same decoded sequence. So I guess what their idea is that you translate both of them into some vocabulary space where this would give you some distribution over that, and this would just be the one-hot embedding, or one-hot encoding, right?
Maybe. Or maybe they just do the normal token-based unembedding. Who knows?
Yeah. So we found that a bit confusing when I was reading that.
Yeah, thank you.
Thank you, Sheba.
You can start introduction.
Yeah, I got my phone more than one time. Okay, so hello everyone. Our project is about one specific paper called Learning to Answer from Correct Demonstrations. And the presentation here we're going to do it's in two parts. First of all, we're going to present the part of the paper that's relevant for our project. And then we're going to show our extension we are working on, which is with a curriculum. We're adding a curriculum learning component to this. So first of all, we have to analyze what do they mean to learn to answer from correct demonstrations. So we're going to go over what they mean by their learning task, their data, and the laws, and finally the learning task itself. So they model a problem of question and answer as a contextual bandits problem. So we'll have X, which is our set of questions, which in this case here is the context, and Y, which is a set of answers, which in this case we are calling actions here because of the contextual bandits thing. And okay, to check if any of those answers here it's correct, we have a reward function, R star, which given pair x, y, it outputs 0 or 1. We have a binary reward. It can have like a half correct answer, just is it correct or incorrect, and that's what this reward means. So we also assume that all of the questions have at least a correct answer. So for every question, there exists a y in which r star is 1. And okay, the data set, we call it, it's a bit confusing in the paper. They use two similar as symbols to refer to the data set and the policy class, but I think we can do it. So this is the set where it have a couple of questions and answers. Okay, and in this case here, X is sampled from D, which is just a set of all the questions, and we have Y, it's sampled from our correct demonstrator. Which is for each xi and a y, it produces a probability of that being that answer being being taken. And this is like an optimal demonstrator. It means it will always get a correct answer back to us. It will not give all the correct answers, just one correct answer. So we can have like multiple different optimal demonstrators here, because a question can have multiple correct answers, but at least one as written here. And okay, this policy here, the correct demonstrator, it is supported by another function here defined as sigma star, which given an answer, it has all of the correct all the correct answers. So this is basically the set with all the correct answers for this specific problem. So this is basically where the data is coming from and the correct answers. So we have the definition of our loss function here, which is for a given data set and a given sigma, which has all of the correct answers. It will output basically the expectancy of how many answers we can get wrong. So let me just write this formula real quick. Okay, so yeah. So our so the laws of a function of a policy pi, given data set D with a set of correct answers, sigma will have its laws defined as the expectancy of getting an answer that's correct from.
That's incorrect.
Yeah.
Is the
Okay,
loss.
yeah, incorrect, because it's the laws, okay, not the reward. So we have here a definition. We have a definition here. That is the rule. Okay. Let's keep this stuff. Okay. Actually, before the definition, we have to go over assumptions we have. So, the main thing of this paper here, we are talking about learning from correct demonstrations, but the thing is, in this paper, they are trying to switch from learning a policy class to learn a reward model, because they argue, they give a couple of examples and try to work out bounds, but they argue that it's much harder for you to learn a policy from an expert than to learn the reward model for that. So they're trying to switch to learn the model, the reward model, and here we have, yeah, what they call the model class assumption. So for the model, which is sigma star, it is inside a policy class S, and this is not to be confused with these S here. They use very similar letters, but they are different ones, which is inside a set with all the possible correct answers, and the policy. It's inside policy class pi, which is inside the set of all the possible distributions between the questions to all possible answers. And they argue that these they argue that the size of the policy is much bigger than the model, and when you try to learn this kind of from a demonstrator, like in imitation learning, when you try to learn it with MLE, the sample complexity, it depends on the policy class size. So this here, and it will take a long time.
It depends on, yeah,
Okay,
the cardinality, yeah.
The policy here, and it will take a long time, so they try to switch to the reward model. And just to finish like the definitions. So if you are trying to learn from demonstrations and you have a learning rule which maps from the product of the sets of x and y, a sequence of that, a empty sequence of that, and it maps into a final policy, which is that distribution here. This space here, then with sample complexity, with the sample complexity, with this sample complexity here, so we are going to have like a sample learning rules. So if we take a number of samples that's greater than the sample complexity, we are going to have that the probability of having our loss of after applying this learning rule, having the loss less than a certain epsilon, it's greater or equal to 1 minus delta. I just have to put in the details here, but this is the definition. So yeah, the probability of getting this loss lower than epsilon will be greater than 1 minus delta. So if delta is a low value, like close to 0, it means we have a high probability of having this lower than epsilon. And this is the basic setup we need from the paper to get into our proposal.
Alright, so just to motivate, I think a few sessions ago, a few people had talked about the PVEC learning is all you need paper from Foster or something. So what that paper talked about was using the MLE rule on the policy class, but this paper argues that the reason to shift to using a model is like if you have a math question and it's more difficult to learn the generation of all the answers to a math question than just to learn the differentiation between what is right and what is wrong. So when you learn this reward model, it is more intuitive, and that is why they have shifted to learning over a reward model. And the earlier paper talked about how MLE was, it was, the complexity was something like.
Wait, can I say something about this?
Yes, please.
I think it's very interesting, this whole idea.
Mm-hmm.
The only little problem, or maybe not so little problem I would see, is that, of course, what happens is that in the application, when you're trying to apply it to math reasoning, the action space is exponentially sized.
Yes.
Right?
Yes.
And so even if you know the reward, there is a non-trivial search problem to be solved. Right? Like taking the argmax over all action sequences that give you a maximum reward, a reward of 1 in this case, is a non-trivial problem. And this paper is doing nothing with that.
Okay.
But you will not be able to do this argmax. So it's like, sure, like, it would be a good idea, but like you still have to learn the policy.
Yes.
You still have to figure out how to find that reward.
Yes. Yeah.
So it just, like something big is missing there.
Yeah.
Okay, anyways, just food for thought.
Yes, yeah. That makes sense, yeah.
they really rely on the policy class being bigger than the model
Yeah.
class. And when they got to the sample complexities, it really depends. Like you look they side by side, it really depends on this assumption.
I know, but like at the end of the day, what they learn is the reward,
Mm-hmm.
and
Yeah.
unfortunately, that doesn't solve the problem of how to act.
Oh, I see.
Yes, yeah, you do need to learn the control, yeah.
Yeah, because like normally, if the action space is so small, this phi is small,
Mm-hmm.
then it would be like, yeah, okay, like just take the argmax, like enumerate all the actions and choose the action that gives you the maximum reward.
Uh-huh.
If you try to do that with sequences
Mm-hmm.
that are for 30,000 tokens per position, and there are 100 positions, what is the number of actions that you need to enumerate over? It's 30,000 to the 100.
Yeah.
Yeah, okay.
Like,
Yes.
it's just like, no,
Mm-hmm.
that's not going to work.
Mm-hmm.
So even though you know what the reward is,
Mm-hmm.
you still have the same problem,
Yeah.
right?
So maybe we can
So
just
it's
go
like
ahead
we're
with
not making any progress
Mm-hmm.
in knowing how to answer the questions.
Yeah.
We know what the correct answer is, like
Yes.
how the correct, like we can recognize the correct answer,
Yeah, okay.
Yeah.
but that
Yeah,
doesn't
in a
make us
practical setting, it wouldn't
be able to
useful.
produce a correct answer.
Yes. Yeah.
So it's like this is a non-trivial amount of work that needs to be done for that to
Yeah.
happen.
So maybe we can just say
Not
that
a little.
the number
what
of
the paper
actions is
does.
like less or something. I think they used 2 in the paper or something, if I'm not mistaken. That is what they use in the paper as well. Like, yeah, I guess
But they
that is.
still talk about language models and reasoning. and
Oh
all
yeah,
that.
yeah, yeah, yeah. That is true. Yeah, yeah.
Yeah.
It won't work there, I guess. But to drive all the work in the paper, they have put like the number of actions is less. I think that is what you said as well. Yeah.
I mean, in general, the idea applies
Yeah,
as
yeah.
long as you can compute the argmax.
Yes. Yes. Yes.
And it might actually show you that like maybe it's better to break the problem into 2,
Mm-hmm.
learn a reward function, and then learn a policy.
Mm-hmm.
So the demonstrations should be used maybe not to learn a policy directly,
Yes.
but
Yeah.
first learn a reward function,
Mhm.
and then somehow learn a policy. But that's non-trivial too, because
It's
you
like
have
a-
this huge exploration problem.
Yes. Yeah. And you need a dual loop, right? Then first to learn the reward, infer the reward function, and then to learn an optimal policy based on that as well.
Right.
So yeah, yeah.
Anyways,
Or
Go
yeah.
on.
Okay. So the paper had the earlier paper was driven by this bound, but the sample complexity is based on, so if the cardinality of pi is like huge, this won't hold, so Emily won't hold in that case, and they prove that even if the model class S is small, like it will quickly just inflate pi a lot. And maybe I can give an example with a bit ahead. But yeah, so I'll just write a bit about how Emily performs with this. And then we can talk about the learners they propose instead of using Emily. And yeah, so what the entire argument is that Emily is good for low cardinality pi, but it fails for a low cardinality of S. So let me just write with the equation for what maximum likelihood estimation is. Okay, so in this case, let us think about how the policy that is trained with like Emily will behave. So the paper talks about it like this. Wait, how did you use the data set? Like this, right?
Yeah,
Yeah, okay.
it's like because on the yeah, like this.
So this is what they have showed how Emily will behave. So given the expert demonstrations data, where you have like optimal x and y, like the correct answers. So if x is observed in the data, like if x is observed in the data, the MLE will just match the empirical distribution and you will probably get a correct answer. However, if x is unseen, so you can choose any distribution over these hypotheses class, where this hypothesis class belongs to a consistent set of S. And how they've defined the consistent set of S is that based on the data of x and y should belong to the hypothesis class of x. So all these hypotheses which contain at least the correct answer for a given x lies in this consistent S class. So maybe just to give an example to make it a bit easier. So let's say if S is this like two hypothesis class, and okay, so maybe to think about what to explain what this hypothesis class means is that like sigma 0 has like 0 as the what it thinks as the correct answer or the valid answer, and sigma 0 1 is the y can be 0 or 1, and let's just say that the true hypothesis or the optimal hypothesis was sigma 0. So based on this, sigma 0 1 is also consistent with, is a part of the consistent set. So because for x, like y belongs to the hypothesis class 0, and like 0 belongs to both these classes, so that means it's a part of the consistent set. And so during test time, if x is unobserved and say you have chosen this hypothesis, like there is a probability you output 1 which is not the correct hypothesis and you fail. So that is how they drive like the failure of MLE. And to go above and beyond this, they propose two learners, which I will just quickly talk about. Okay, so the first learner is the sample inefficient learner. So what this tries to do is that, say you have like a set, like you have the rewards, you have the model class S, and it has it's a set of all these hypotheses. What this does is, it just tries to find out the majority vote for what all the hypotheses think is the correct answer. So it's like, it returns a majority over this model class S, where you return majority X, which is just the argmax Y over the entire thing, such that you want to maximize the number of consistent hypotheses. So this is the sample inefficient learner. So it's like at each stage, so and they pose it as a contextual bandit problem, I think, as Pedro mentioned. And yeah, I think I can talk about how they do this. So they don't, it is a contextual bandit setting, but they do differ in one part, where it's like at round 1 to D. So the first thing is you learner receives arbitrary X and learner then outputs So the learner receives an arbitrary x, and through whatever through whatever learner it is, it outputs yt hat, and then the learner receives a true demonstration, like the correct demonstration, and the only change is that the learner does not know if this is a mistake or not. It just receives a correct demonstration, and it can be unrelated. So this is where they diverge or have a difference with the contextual one. Is there a question, Chava?
This makes sense.
Okay. Alright. So, yeah, and they have some proof over the sample complexity and the number of mistakes. So, the sample complexity is like cardinality of S into log S, which is, S is not the data set, it is the size of the reward model. And the maximum number of mistakes it can make is S minus 1. Okay, and a mistake is such that the prediction does not lie in the true hypothesis class. So this is the sample inefficient learner, and you can have the sample efficient learner, and they have like a not a similar algorithm, but somewhat same, and they just tweak one more thing where it's like you initialize. Okay, I think you don't have a lot of time, so I won't talk about the sample efficient learner. I'll talk about what we wanted to do. So just trust me when I say the sample complexity of the efficient learner was log S, and the max mistakes it could make were log S again. So okay, so something that we thought we could do is that what if we can change this and give xt in a more smarter way? Instead of the learner receiving an arbitrary xt, maybe someone forms like a curriculum based on somehow what we did. So we wanted to investigate what happens when we change this, and the main idea was that we want to prune all the false hypotheses as fast as possible from this class S, and we thought about having like a disagreement variable, which is
Gotcha. Yeah, that's fine.
oh, okay. So it's like and okay, so just to make it a bit easier for ourselves, let so let the it's a singleton set, and it can only contain 0 or 1 for all xt. So yeah, and let sk be the size of model class at k stage, and we defined mk and nk. So mk is the, this is a rough. So we are just counting the numbers of like 0 and 1s over here. It's probably better to write this, but yeah. And we defined this splitting or disagreement variable as a maximum over so we want to find what is the most fraction. So okay, we want to choose an x such that we can eliminate the biggest fraction of the hypothesis based on this, and we Yeah, okay, so what we came up with is, I'm not sure how correct it is. So we defined like at stage k and k plus 1, so this will be greater than 1, and we defined this as r k. Yeah. So it's like to drive down from sk to sk plus 1, the size, we have like this elimination variable called rk, and if we assume that at the end, so like what this is similar to, oh, I made a mistake, it should be epsilon. So what this means is, for the efficient learner, for if the size of the reward model hypothesis class is S, to drive it down to like a low error, we need this much sample complexity. So we just thought that this is at like each stage. Okay, so it should be like log S should be equal to log rk. So because you are keeping on eliminating rk, like at the end, if you are just left with ideally one hypothesis, this should work out away. And we just thought that for each stage, the sample complexity should be like log of rk upon epsilon k. So epsilon k is like a tolerance error, what we thought of, and at the end, so
what's mk? What's the small mk?
oh, this is like the sample complexity, or the number of samples needed for k stage to get this error, to get to this error. It's like S we are replacing with this rk thing.
Okay.
Yeah. So it's just similar, and we are just adding over, so like M curriculum, like the total number of samples needed, we thought should be just an addition over all these things. So this is what we thought about. Yeah. We are not sure.
I think it's really interesting. Obviously, there's been quite a bit of work on active learning, and this would be one instance of that. And, people were looking at this, starting with little stones, general optimal learner that looks at similar things, right?
Yeah.
And so one thing, I guess, like there are some details that need to be worked out properly here.
Yes.
It's interesting, but there was one more thing that is of interest to me as a variation. So this sounds like the default variation of the problem, where the learner doesn't know what they need to learn. I'm also interested in the case that there is a teacher who knows what the learner knows and who knows what they want to teach.
Yeah.
And they are thinking about the next example
Yes.
to be given to the learner.
Yes. Yes.
And I
Yes.
think that would be super nice to look at, because in the setting we are in reasoning, we actually do know what we want to teach, and we can also open up maybe the learner and know what the learner knows. And it would be really nice to see whether, like if the learner is trying to figure out what example to look at next, but they are unaware of what they need to learn.
Yes.
How much more efficient could it be
Yes.
if the teacher, who is informed about what they want to teach and also informed about what the learner knows,
Yeah.
can do,
Yes.
right? Like
Yes.
the gain that you could get from that setting. And I think that generally that is the practically important case here. Because I think that the gains are huge.
Yeah. Yes.
Just an idea.
Yes. 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 Yeah.
Okay.
Yeah.
Even it's kind
Sounds
of
good. I
interesting.
don't say that I understand all the notation that you have, because it seems, I don't know. But maybe there is not that much time, we can take that offline, but I kind of know what you're going after, and that's a sound idea.
Yeah.
So, yeah.
So it was, I mean, I think the curriculum, as you said, like active learning is probably a better wording to use because it's a lot on disagreement. So
Exactly.
yeah,
Exactly.
yeah,
So that literature is the relevant literature.
yeah, yes,
And yeah. Okay. And but the variation that I think is interesting and new, people didn't really look at that, is when, well, okay, so that's not true. Like I know some literature where like that's old literature, they're talking about teaching dimension. But the teacher tries to be smart about what the student knows and what to show the student.
yeah,
But usually that gets into like some really complicated things. And here I think you have a chance to do something simple, which is also effective and could also be practically relevant.
yeah,
So I think that will be pretty exciting to do.
yeah.
Yeah, I
sounds
think
good.
it's interesting if you think about how we can learn that teacher.
Yeah.
You know.
So this was probably just one method, like making max, like the disagreement kind of thing. But yeah, I think we can, yeah. Yeah. Yeah, I mean, that's it for our presentation.
Thank you guys.
Thank you. Thank you, Chava.
Jacob.
Thank you.
Yeah, thank you. Bye-bye.
Bye, everybody. See. See you.
Just have to